My name is Sambayeva Adiya, and today I'm going to explain you IB Chemistry, units 3.1 and 3.2. It's also called periodicity, and here are the understandings mostly, and we will cover some of the applications, and we will cover it during the presentation, so you should not really read this. So the first one, periodic table and electronic configuration. The first thing IB wants you to know is that the periodic table is arranged into 4 blocks associated with the 4 sublevels. They are S, P, D, and F. As you can see here, metals are and helium, they are in sublevel C. Then transition metals are mostly sublevel T. Non-metals and metalloids are sublevel P, and here also we have sublevel F that we don't really will cover like in details, but you have to know this. Second one is that the periodic table consists of groups, vertical columns, and periods, horizontal rows. So as you can see, for example, here, the periods are, the first period is colored in red, the second is in orange, the third is in yellow, and etc. And here you can see the first group, second, then like transition metals, and for example 13, 14, 15, 16, 17. These columns are called groups, and the horizontal rows are periods. Then the period number n is the outer energy level that is occupied by electrons. So for example, let's take hydrogen. It has only one energy level, that's why it's in period 1. And for example, here you can see blue color, it's period 6. And these elements have 6 energy levels. Next one is deduction from periodic table. The number of the principal energy level and the number of the valence electrons in an atom can be deduced from its position on the periodic table. Here is an example with magnesium. As you might know, magnesium has 3 outer shells, and this is why it's in period 3, and also has 2 valence electrons, so this is why it's in group 2. And here for you to understand, principal energy is N, and valence electrons are the electrons in the outer energy level. Next, position in periodic table. The periodic table shows the position of metals, non-metals, and metalloids. So as you can see here, the red colored elements are metals. Then we have some of the metalloids right here between metals and non-metals. And here are our non-metals. And you also have to know physical properties as well as chemical. Here are physical properties of, for example, metals. They are solid, ductile, they have metallic luster, they are malleable, and they are, as you might know, good conductors. Then non-metals can be solid, liquid, and gas. They are dull, brittle, and are insulators. And here are metalloids. Properties, they have properties of both metals and non-metals. They have metallic luster, brittle, and like semiconductors. And also, the number of metalloids might change because sometimes there are 6, sometimes there are 7, but the main are here. So basically, it was unit 3.1. So let's move to to the unit 3.2, and here is our understanding. Vertical and horizontal trends in the periodic table exist for atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. Here you can read the definitions, but we will cover them later in presentation also. And also I wanted to add two definitions that are not in the understanding that IB gives us, but it's really important for you to know this. These are effective nuclear charge, the attractive positive charge of nuclear protons acting on valence electrons. So actually it's like nuclear charge, but we're considering its effect only on the outermost energy level. And the second definition is electron shielding. Electrons closer to the nucleus shield the electrons farther away from the positive charge of the nucleus. This one is pretty clear, but if you don't understand, we'll cover it later with some pictures. And also wanted to mention that you have to know these definitions by heart, because the main words, key terms here are important for you when you will answer to the open questions or to multiple choice. So you better to learn this. The first one it's atomic radius. And atomic radius halves the distance between the nuclei of two bonded atoms of the same element. And here you can see periodic table. And let's look at period 2, for example. Here, as you can see, as we go from the left to the right, the atomic radius decreases. And as we go from the top of the group to the bottom, it increases. So this trend can be explained by two main points. First one is nuclear charge. It can be explained on the example of periods, for example. As we go to the right, across a period from the left to the right, as you can see, the atomic radius decreases. And the reason is that nuclear charge increases. However, the amount of shielding doesn't really increase, and the increasing nuclear charge affects atomic size, since nuclear charge attracts more electrons, and this makes the atom size smaller. And the second one is electron shielding. It can be explained on the example of groups. For example, let's look at the first group. As you can see here, as we go down, the atomic size increases, and the reason is that as we go down group, the number of energy levels increases, and this is the reason why atomic size increases. Second one is ionic radius. Ionic radius is the distance of the outermost shell of electrons from the nucleus of an ion. Here, the main trends is that ionic radius increases as you move from top to bottom on the periodic table, and ionic radius decreases as you move across the period from left to right. So the trends actually are similar to the atomic radius. However, here is one thing that you have to understand. For example, as you can see here, boron has a lower ionic radius than oxygen. It might be confusing because boron is on the left, so therefore is like located more to the left, while oxygen to the right, and oxygen is supposed to be lower, supposed to be smaller. However, the thing is that boron ion already donated 3 electrons, and so there are less electrons, and nuclear charge the effects on the electrons that are left, and therefore the radius is smaller. One When it comes to oxygen, as you can see, oxygen gained 2 electrons, and this is the reason why the ionic radius is more huge, because the nuclear charge that affects the outermost energy level and valence electrons is not that, it doesn't attract electrons because it gains 2. So this is why the radius is bigger. And here are the aspects ionic radius depends on, and they are actually the same as in the atomic. So here, as we go down, the group shielding increases, and that's why ionic radius increases too, and nuclear charge increases, and this is why the radius becomes lower. Next one is ionization energy. Ionization energy, the first ionization energy of an element, is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. You have to know this definition and do not forget about the key terms like 1 mole of electron and 1 mole of gaseous atoms. These key terms are really important during IB exam because I can really explain a lot of things knowing this definition. And as you can see on the left picture, ionization energy increase as you go from the left to the right across period, and it decreases as you go from the top to the bottom of group. And here ionization energy is affected by 3 main things. First one is atomic radius, and as you can see, the atomic radius increases down the group, and this is why ionization energy decreases. And the reason is that nuclear charge can't really pull the valence electrons, especially when the shielding, the number of energy levels increases. Yes, and this is why it's easier, we can say, to pull the electron of, for example, potassium than the electron of lithium. So it requires less energy. Second one is nuclear attraction, and here, for example, let's take the example of nitrogen and oxygen, for example, from nonmetals. And here the nuclear attraction of it would be better to take, for example, lithium and beryllium. So here, as you can see, nuclear attraction in beryllium is higher because it has more protons, and this is why it's harder to take the last electron from beryllium than from lithium. And the last one is electron shielding. Actually, at this point, atomic radius and electron shielding are similar, because as you go down the group, number of energy levels increases, and this is why ionization energy decreases. So here is a little bit difficult thing for some people, might be. So here, as you can see, the ionization energy is not that consistent, and as you can see, it drops or goes higher, and etc. And to understand this point, you have to have some basic knowledge about electron configuration. And as you can see on the top picture, Here's for example, here are for example electron configuration of some elements. And let's take for an example lithium and beryllium, as we did before. For example, as you can see, lithium has lower ionization energy than beryllium, first ionization energy. And the reason is that it's easier for an electron to take this one electron from 2C group than to take 2 electrons from this group, because when it's paired, actually it takes more energy to pull out the electron, and this also can explain some other elements. For example, let's take nitrogen and oxygen. Here, as you can see on the bottom picture, nitrogen has 3 electrons in the 2p group, and oxygen has 4. And for example, let's take a look at nitrogen. As you can see here, nitrogen's 2p group is full, even though the electrons are like alone without a pair, but the fact that it's full and there are no more electrons in this group makes it more difficult to take out the electron. While for example, for oxygen, as you can see on the left picture, oxygen's first ionization energy is lower. For oxygen, for example, as you might know, the one electron is goes as pair in 2p group for the first place, and here you might think that there are more electrons, and you can think that the ionization energy has to be higher. However, when there are 2 electrons in 2p, like in one place, here we can call it home, in one home, and other ones are alone, it actually makes it easier to pull out the electron that is in pair than to take electron from nitrogen, for example, from the third place. So yeah, it might be a little bit difficult to understand, but the thing that you have to know is that it's easier to pull out electron when it is pair, while other are not, than when they are all alone in one sublevel, like 2p. And here you can see this diagram with more elements. And here, as you can see, on the top there are noble gases, and you can see they have the highest ionization energy. And the reason, as you might guess, is that noble gases are full and all of their energy levels are full, so it's really difficult to for example, here you can see it's really difficult to pull out this electron, because as you can see, they are all paired and the 2p sublevel is full. So yeah, it takes more ionization energy. And the next one is electron affinity. The definition is the energy change when 1 mole of electron is added to 1 mole of gaseous atom to form 1 mole of gaseous ions. So actually the definition is pretty similar to ionization energy definition. Here we also have 1 mole of electron to form 1 mole of gaseous atom. But here we have 1 mole the energy when 1 mole of electron is added to 1 mole of gaseous atom, and to consequently form 1 mole of gaseous atoms. Actually, it's like a little bit like vice versa to first ionization energy. Here are the trends. Electron affinity values generally get more negative as you go from left to right in a period, which means that the halogens really want to add that extra electron. So as you can see, the electron affinity increases. Halogens, for example, fluorine, they have one of the highest electron affinity, and this means that they can pull electron from other atom or ion, for example, easier than it can do, for example, beryllium or lithium. And the reason is that fluorine needs only 1 electron to be full and to reach the state of noble gas. And as you know, all electrons are trying to get their energy levels full. The patterns vary down a group and do not show the same clear trends as do atomic radii, ionization energy, and electronegativity. But like in simple words, as you go up from in a group, the electron affinity also increases. And the last one is electronegativity. I think you already heard this in MYP, and you're familiar with this concept. The definition is electronegativity is a measure of the tendency of an atom in a molecule to attract a shared pair of electrons towards itself. And as you can see on these pictures, the electronegativity increases as you go up in the group, and it increases from the left to the right. And electronegativity can be explained by nuclear charge and atomic radius. So as you can see, as you already know, nuclear charge increases when you go to the right, and this is the reason why electronegativity is higher, because an element or like an ion has a higher ability, more nuclear energy to nuclear charge to pull the electrons, and this is why electronegativity is higher. Here, as you know, electronegativity is a measure of tendency of an atom in a molecule to attract shared pair of electrons. And I'm sorry, it can be also explained by atomic radius. So here, as we go down group, for example, second group or the first group, here's the atomic radius as well as electron shielding increases, and this is why nuclear charge cannot really pull the electrons, and this is why it cannot pull shared pair of electrons towards themselves, and this is why electronegativity decreases down the group. And here is a picture of everything, of mostly everything I have explained you. Here is, you can see ionization energy, electron affinity, atomic radius. Here is now ionic radius, but the trends of atomic radius and ionic radius are pretty similar. And here are non-metallic character and metallic character. So as you know, on the right part of periodic table, there are more non-metals. There are usually like non-metals and metalloids, and on the left there are transition metals and just like metals. So this is it actually. Thank you for your attention.